Hello, everyone. My name is Shahriar Afkhami, and I'm a researcher from Lund University, and I'm here today to present one of our research studies with collaboration with University of Oulu on additively manufactured stainless tool steel. But before getting into the results that are the main focus of this research, let's have a brief introduction on the studied material. The material and the metal powder designed for 3D printing is commercially known as EOSCX, a metal powder developed by Electro-Optical Systems. And it has chromium, nickel, and molybdenum and aluminum as its main alloying elements. And the presence of course, chromium, nickel, and aluminum are the most important ones, as I will explain later. So in its nature, it's a stainless steel, considering the high amount of chromium, and of course, considering its hardness values in the range of 300 to 450 vickers, it's considered as a tool steel. And the combination of high corrosion resistance and hardness make it a very versatile material. And another great point about this material is that it can be processed via additive manufacturing. And considering this, it has a low carbon content to make it being able to be processed by additive manufacturing methods like laser powder bed fusion, and inherently such a capability make it also weldable. It is heat treatable. It can be hardened by a precipitation hardening with the edge hardening procedure, and its background phase is more transitic. So in nature, it's a more aging steel. And because of all these great characteristics, it can be vastly used in aerospace, marine, automobile, petrochemical, and nuclear industries. However, the importance of this material and similar other powders is that they literally divide the precipitation hardening steels that can be processed by additive manufacturing into two different eras: before the emergence of these materials and after that. Before that, we had these classic 17.4 pH, 15.5 pH, or 18 nickel 300, which is commercially known as MS1, as the metal powders that are considered for 3D printing, and that can be used as tool steels. And the high hardness of these steels after heat treatment heavily relies on these kind of complex compounds that are comprised from, for example, iron, molybdenum, or nitride particles. However, the problem was that these kind of particles have limited stability at high temperature. So to resolve these issues, the next generation was developed by companies like EOS or Odeholm, and they used beta nickel aluminum particles to make these materials precipitation hardening. And the good point about these beta particles is that they are very coherent toward the background phase. The coherency index is close to 100%, and they are more stable at high temperatures, maybe even as high as 400 to 500 degrees. However, these kind of high level of coherency make them very difficult to detect in the material. For example, at Dodzoden and his colleagues had to go to these extremely high TEM, high magnifications to, in practice, detect these particles, 1 or 2 nanometers particles, and they do a high coherency, even micro or nanostrain are not an option to detect these kind of particles in the background phase. And of course, this high magnification SAD pattern to confirm their presence in CX after heat treatment. Okay, so some of the results from our previous studies, of course, confirm the microstructure of these material after 3D printing as being martensitic, both in its as-built condition and even after heat treatment, the martensitic structure remains. However, after heat treatment, there is a slight difference between the texture and features, the size of the features in the microstructure. As you can see in this EDST results, the left side are for the as-built material and the right side are from after heat treatment. And heat treatment caused a difference in the balance of the grain boundaries and low angle grain boundaries. And of course, in addition to the martensite in the background phase, we also detected some minor amounts of retained austenites as red dots in this image, and the amount was below 1%. However, this below 1% retained austenite can have an important role in the mechanical performance of this material, as I will explain later. And of course, after heat treatment, we can observe these nanometric particles, beta particles that have a huge contribution to the strength of the material. So these are the general aspects of the microstructural feature of this material after additive manufacturing and after the heat treatment that is designed for this powder. And as you can see, the effect of heat treatment on the quasi-static mechanical properties of these materials is significant. It causes huge significant increase in the strain values from around 1,100 megapascal to close to 1,600 megapascal. And even after heat treatment, as it is shown here, the amount of ductility and elongation to failure of the material is significant. As you can see in this DIC image, even the heat-treated sample showed a very significant necking phenomenon before its final rupture. So combination of ductility and high strength is a perfect combination for many mechanical applications. And of course, we have the strain hardening aspects of this material as its major properties. In the as-built situation, we can detect a recovery stage in this material, which is not present in the heat-treated version. And this recovery stage, later we contributed this slight recovery to that below 1% retained austenite in the microstructure. That's why it is so important from our perspective in the material, although the amount is minor. And after that, we try to evaluate the fatigue performance of the material. And one interesting aspect of these materials, these precipitation hardening materials, is that all the precipitation hardening causes a huge increase in their quasi-static mechanical performance. In significant amount of cases, such edge hardening procedures doesn't show a noticeable increase in the fatigue performance of the material. The fact is that the high strain of these materials after heat treatment relies on the presence of these micro nanoscale precipitates. On the other hand, material become more defect sensitive, and even in some cases, these precipitates that are supposed to contribute to the high strain of the material can act as failure sites for the fatigue, especially in high cycle fatigue performance case studies. So if you test CX after heat treatment, MS1, or even in some cases in 718, and you don't see any kind of improvement in the fatigue performance, don't be surprised. This can happen. And even you can see the failure initiation size in the as-built and heat-treated version. They are similar. The size of the defects and their presence are similar to each other. And after all of these, let's get into the focus of this presentation, the mechanical performance of this material under high temperature. So as you can see, in the as-built version, up to 500 degrees, no significant change is apparent in the strain of the material. However, After 500, there is a sudden decrease down to 800. The dialectometry results of this material from our previous studies shows that this kind of temperature range is the range that can cause a precipitation solution in the microstructure. However, a high number of beta particles are not expected in the as-built version. So in this case, I think the tempering effect of the background martensite is a dominant factor, which is also manifests itself in the decrease in the ductility because of the presence of carbides, but it's a low carbon still. So the influence is not that much significant, but it's still there. But in the heat-treated version, before going to that, we can also consider this the effect of residual stress after 3D printing from based on our previous results. The samples after 3D printing show significant amount of residual stress. The samples used for high temperature tensile tests were built in horizontal direction. So if they are exposed to heat, these kind of compressive residual stress values can be go to 0. So it can also have an influence on these results here. And if you compare the behavior of the material in different temperature in this as-built version compared to the heat-treated version, the heat-treated version had a more normalized behavior. We believe that's because the heat-treated version is strength and ductility heavily relies on the presence of beta particles, and its strength starts to decrease because by increasing the temperature, the solubility of these particles increases and they vanish from the background structure. Combination with the tempering effect of the martensitic phase cause this kind of smooth decline in the strain values and on the other hand, increase in the ductility. From fractography perspective, as I explained before, up to 500 degrees, there are differences between the as-built and the heat-treated version, as you can see here. But above 500 degrees, the difference is no more there because practically in 500, 600 degrees and above, the material doesn't matter if it is as-built or heat-treated, it's the same. And in the case of as-built samples, the damage was fully ductile. As you can see here, even close to the shear lips, there are the signs of ductile failure are apparent, except for these kind of huge voids that we believe they're initiated by these detected aluminum oxide particles that were randomly in the microstructure. However, in the heat-treated version, the fracture was quasi-clivage or semi-ductile. The presence of some kind of intergranular microcracks were also apparent. And in the scale of micrometer, we also detected some brittle clivage failures. However, the presence of was not that apparent that caused a brittle fracture in the specimen. And this is an ongoing research, so this was the most difficult part for me to make a concluding remark. But based on what we have here and our results so far, we can say at high temperature for the as-built specimens, a complex mixture of tempering, recrystallization, and grain growth, and of course, particle precipitation and dissolution contribute to the material behavior, while for the heat-treated version, the mechanism is simpler. The precipitation, dissolution, and tempering are the main factors. Fractures practically were ductile regardless of the material situation. For the as-built material, it can be used up to 500 degrees if we consider the strength of the material as our criteria, as it is recommended in many marketing, of course, data sheets. However, considering the smooth decline of the strength for the heat-treated version, defining a safe temperature might be a little more arduous. Thank you very much.